Kirsten Eisenträger is a professor of mathematics at Pennsylvania State University. She received her PhD in mathematics from Berkeley in 2003 with a thesis on generalizations of Hilbert's 10th problem concerning decidability of Diophantine equations. In addition to further results on Hilbert's 10th problem, she is known for her research on computational number theory and arithmetic geometry with applications to cryptography, such as isogeny graphs, construction of genus 2 curves, efficient elliptic curve computations, pairings, and lattice problems. She will speak to us today on algorithms and reductions for isogeny problems. Okay, go ahead, Kirsten.
Thank you very much for the introduction, and I'd like to thank the organizers for giving me the opportunity to speak at this workshop. Let me make sure the, okay, let me just see why it's, let me try once more. I'm not sure why it's not liking the, okay, that's looking good now. I would like to talk today about algorithms and reductions for isogeny problems, both in the quantum setting and in the classical setting. And I am spending the year as part of my sabbatical at the Simons Institute in Berkeley, which has a quantum research pod. So bringing together people from various departments, computer science, physics, chemistry, and also mathematics to work on exactly these kind of questions. So I'm excited to give a talk at this workshop about this. And I also appreciate that since I'm on the West Coast, that the organizers didn't give me the 7 a.m. California time talk slot. It's fine to listen to talks at 7, but giving one is more challenging. So let me start here. So all of this is really motivated by post-quantum cryptography. So let me just briefly review what the goal is. So the goal is to develop public key cryptographic algorithms that are still secure in the presence of quantum computers. It's easy to list what the bad choices are. The bad choices are obviously RSA, also traditional elliptic curve cryptography. And the big question that post-quantum crypto hopes to answer is what the good choices are. And so we've already seen one talk about lattices this morning, and the majority of the systems that have been proposed for post-quantum cryptos are based on lattices and some version of like either LWE, ring LWE, module LWE. There's also code-based crypto, like I'm just going to list Mikulicz, and then there are isogeny-based systems. And in this talk, I am going to focus on isogeny-based crypto as a candidate for post-quantum crypto, and sort of discuss what's possible and sort of what the landscape looks like. So I'm going to state several different problems, the equivalent ones that are the underlying hardness assumption here, and sort of discuss where it might be possible to make progress with a quantum algorithm, and where, in which cases progress has already been made. So So let me just start by mentioning how elliptic curves first showed up in cryptography. So I'll refer to this as traditional elliptic curve cryptography, usually just called ECC. And so that was proposed by Neil Koblitz and Victor Miller independently in 1985. And if you believe Wiki, they claim it's been widely used since 2004. I remember that in the beginning, early 2000, people were still asking, well, are these elliptic curves used anywhere? And so certainly for the last 20 years or so, they've been everywhere, except especially on small devices like cell phones, cryptography on cell phones or other devices with small storage. The traditional elliptic curve cryptography is based on the hardness of the discrete log problem on elliptic curves. And it is broken by Shor's quantum algorithm for discrete log. So with a quantum algorithm, you can break these and systems, and the object in these systems is an elliptic curve defined over a finite field. So I'm thinking, when I'm saying elliptic curve, I mean, I'm thinking about an equation of the form y squared equals x cubed plus ax plus b, where a and b are in some finite field. And if we add in a point at infinity, we get an abelian group. And there's a beautiful group law that can be described both geometrically or through just explicit equations to figure out what the sum of points looks like. But so the main thing that we're using is that the points together with infinity have a group structure, an abelian group structure. And so in traditional ECC, we use one curve in a specific instantiation. We assume that discrete log problem is hard for the group of points on this curve, and the advantage is that we get small key sizes. Since Shor's algorithm breaks these, the new system that still uses elliptic curves now has a different underlying hardness assumption. And this time, we're not just using one elliptic curve, we're using an exponentially large set of elliptic curves. And we're interested in the isogenies between them. So anyone who's not familiar with isogeny can just think maps. And in the following, even though I'm only going to define it a little bit later on, I'm going to use the terminology supersingular elliptic curve to make some of the statements I'm making correct, but I'm only going to actually need the properties of them a little bit later on. So, okay, so one question would be, why are we even looking at supersingular isogeny-based crypto? And on an earlier slide, I had the pool of potential post-quantum candidates. And I said I'm listing a few, but I basically listed representatives of all of the proposals there are. So there aren't that many ideas or many different ways that people propose to do crypto that might be resistant to quantum computers. So it's really impossible to, it's really necessary to actually investigate all of them. And of course, so I really like elliptic curves. They've been used in crypto already for more than 20 years. So a lot of people have studied them. And there's infrastructure in place already from all the elliptic curve from the traditional elliptic curve crypto. And so this is a very familiar object. Some of the underlying computational assumptions have already been studied. For example, computing endomorphism rings, that was already done, for example, in a thesis by David Cole, who looked at this problem computationally, so in '96. So this is not, so these are things that have been looked at already. Well, so what are the concerns? The systems are very new, so they have not been scrutinized as much as some of the other systems, like the lattice-based systems that have people have studied much more. And another issue is that compared to lattice-based crypto, we don't have all of the functionality. So for example, there is no fully homomorphic encryption, at least as far as I'm aware, coming from isogeny-based system, and we don't have things like identity-based cryptography. So here, just to sort of give an overview of where we are in the landscape of public key crypto. So there's RSA, that's built on the hardness assumption that factoring is hard. Then there's ECC with discrete log. Then we have LWE or ring LWE that's uses the assumption that the shortest vector problem in lattices is hard. And we've seen a talk related to that and bounded distance decoding this morning. And then there are the isogeny-based systems that I'm writing two categories, ones that have a class group action and ones that don't. And then there's also sort of, I'm listing soliloquy as like one of the sort of outlier lattice-based systems that have been broken by quantum computers. So so that was built on the hardness assumption that the short generator principal ideal problem is hard, but that turned out to be not the case. And that's related to computing unit groups in quantum polynomial time, which is possible. Yeah, sort of generalization of the problem that was solved is a generalization of work that came out of the Pell equation by Hallgren and then led to the result on the unit group by Kitaev, Song, Hallgren, and myself. So how long have these isogeny-based systems been around? Well, the hash function based on supersingular isogeny was proposed first. That was proposed in 2006 by Charles Gorn and Lauder. And then there's also a system based on ordinary elliptic curves that's mentioned in this setting. But then the real main one that we're talking about today is supersingular isogeny Diffie-Hellman, which was proposed by David Zhao and Luca De Feo. David is going to speak tomorrow, I think. And so that's usually just referred to as SIDH. There's commutative versions of that. And then there are also people who added an orientation. But if you look at the dates, quite a few of them have been proposed in the last 5 years. So this is all very recent and very much work in progress, how hard these are or what can be done with them. So I'm drawing an arrow here, sort of they usually get divided into two categories, ones that use the full set of supersingular elliptic curves, and then ones that use a subset of them on which we can define a group action, which I'm going to make more precise now. So let me say a little bit about that. So what is sort of the status of security for these isogeny-based crypto systems? Well, because they've been studied much less, I feel like it's really too early to have confidence in security or like either direction. And it's not just against quantum at this point. I feel even classically, there's still a lot that needs to be done at this point. And so when we started looking at this a few years ago, one of the things that sort of stood out was that like a couple of different signature schemes were out there that used different hardness assumptions. One was, and I will talk about that, was the existence of finding isogenies between two specified curves. Then there was the question where the secret was a certain maximal order in a quaternion algebra associated to an elliptic curve. And the question first question sort of was, how are these hardness assumptions related to one another? And is there some different way of studying the hardness assumption that might make them more accessible to, or where we can get input from people working in other areas? Also, for some of the objects, I mentioned, for example, maximal orders in quaternion algebras, there are sort of many different representatives one could choose. There's not necessarily a canonical one, and it wasn't even clear whether there actually is one or of a small size, polynomial size. So if you're gonna find a polynomial time algorithm for something that outputs, say, the maximal order, you at least want to know that it has polynomial representation size. Otherwise, that question doesn't even make sense. So, and so those are sort of some fundamental questions that have to be answered before you even try doing anything with a quantum algorithm or classical algorithm. So sort of these sort of basic questions have been answered mostly. So, so we can show that isogenies, endomorphisms, maximal orders that are showing up, that you can find polynomial representation sizes for them. For some of the maximal orders, you need GRH, but you really have to be careful how you represent things. For example, the isogenies that show up will have very large degree, and you really do have to decompose them to get something that you can write down. And also, I will talk about the reductions that exist between the different hardness assumptions in the systems that have been proposed. So this is, the first is joint work with Holgren, Lauder, Morrison, and Petit from 2018. And the second is from the same paper and then was extended using fewer heuristics, in fact, removing all of the heuristics except GRH by Wesolowski in 21. So what are the computational challenges here? And so I will be talking about the supersingular L-isogeny graph. All my isogeny graphs today are going to be supersingular, so I'll still mention it occasionally, but SIDH, which is the earliest supersingular key exchange, uses all of the supersingular curves, so it uses the full isogeny graphs. And the schemes that have group actions, it's not a subgraph, but the graph that can be constructed for those has fewer vertices, but still exponential, meaning something order of magnitude p or square root p. And so what is the key property that all of this is based on? Namely that the isogeny graph involved is an expander graph. And again, the curves that we're dealing with are very nice because they're super singular. We can pick the A and the B that describe the curve equation just in FP squared. So they have small representation size, and that's one thing that gives an advantage for using supersingular curves. But even if we have two curves that are defined over a small field, if we look at maps or isogenies between them, those can be defined over really large extension fields, and we might still end up with exponential size objects if we're not careful. And I already mentioned that one thing to do is to not write down the isogeny just as one piece, but to decompose it as a sequence of isogenies and give that and write that information down. So I mentioned the supersingular isogeny graph. So here is a picture. So I'm fixing my prime P. So that means everything I'm doing is happening in characteristic P. And P is going to be a very large several hundred digits, say. But the L that I'm using is going to be very small typically. So in SIDH, L might be 2 or 3. So, so I'm looking at all of the supersingular elliptic curves in characteristic P. I know there's roughly P over 12 of them. So if P is my prime of cryptographic size, then this gives me an exponential size set of vertices. And the graph is an expander. And locally, everything is very nice. So if you give me a vertex, I can efficiently compute its neighbors. But the thing I really want to do, or that I would have to be able to do to break, for example, the crypto system or the key exchange proposed by David Zhao and Luca De Feo, would be a problem of the following type. For example, if I give you E, the curve on the left of the picture, and I give you the equation for E double prime, I want to find an isogeny between E and E double prime. And I also want to say, specify its degree, that it should have L power degree. So that's going to be the problem that will have to be hard. So locally, if you just tell me, compute all the neighbors of a given vertex, that I can do. But the hard problem is going to be given any two curves, connecting them by a path. So let me just, I've already said it, but let me make it, let me write down the definition. So the vertices are supersingular elliptic curves up to isomorphism in characteristic P. And the set of edges, so we're going to connect two curves by an edge if there's an isogeny of degree L between the two curves. And so L is the size of the kernel here because it's co-prime to the characteristic. And whoops. For example, when L is equal to 2, So that means the kernel will have, I'm looking for isogenies whose kernel has order 2. There are 3 subgroups of the elliptic curves of order 2. And so that means if L is 2, then my first vertex is going to have 3 edges going out of it and so forth. So I'm actually, except for 2 exceptions, 2 J invariance exceptions, I'm going to have L+1 edges coming out of each vertex. So, and so again, so here is the problem that we're looking at. So we have a curve E. We have another curve E prime, and what we would like to do is we would like to find an isogeny of L power degree that connects E and E prime. And the picture that I've drawn here is for L equals 2. So we have E connecting to 3 curves, E1, E2, E3. And it's easy to compute those 3 curves. But the hard problem is finding some 2-power isogeny between E and some other curve E prime. We do know the graph is connected, so we do know it exists, but so finding this is the hard problem. And so let me just formalize this. So the hardness assumption that some of the systems are based on, for example, SIDH, is what we call the L isogeny pathfinding problem. So we have the input are 2 supersingular elliptic curves, E and E prime, and we want to find a path from E to E prime in the L isogeny graph. And if you want to solve this problem, the fastest classical algorithm between them is O tilde of square root P by Delfs and Galbraith. And so that's not yet the L power case. That's just constructing isogenies between 2 given supersingular elliptic curves. And here, so what can quantum do in this situation? That can do a square root speed up. And it's a result of Biast, Zhao, and Zenkar. And it uses Grover's algorithm. So that's where the square root speed up is coming from here. And it goes through first finding a path to an elliptic curve that's defined over a smaller field, then connecting those, and then connecting the path back. And that gives a square root speed up of O tilde P to the 1/4. The tilde just means that there are some log factors that I'm not writing down. But so the best known classical and quantum algorithms are exponential for this problem. So now, then the question is there something else we can do? Can we reduce it or show to some that it's equivalent to some other problem? And yes, we can. So looking at other problems, one can actually show that the pathfinding problem is equivalent to computing endomorphism rings of supersingular elliptic curves, and also to computing the associated maximal orders in quaternion algebras, which I'm not gonna define right now how we do this association. So when I'm saying endomorphisms, I just mean a map or an isogeny from E to itself. And the endomorphism ring that's just the set of all isogenies from E2 itself. It has a ring structure. And here is where where it matters that our curve is supersingular, because when the curve is supersingular, the endomorphism ring is a Z module of rank 4 or a lattice of rank 4. So it has, whereas in the non-supersingular case, in the ordinary case, it just has rank 2. So here we have a Z lattice of rank 4. And so that means the endomorphism ring problem then can be stated as follows: given a prime P and a supersingular elliptic curves, like let's say I've specified it so that it already has coefficients in FP squared, I want to find four endomorphisms that generate NE as a lattice. So I want to write so I see there are a couple of questions in the chat. I'm not going to be able to, so basically the endomorphism ring of a supersingular elliptic curve is isomorphic to a maximal order in the quaternion algebra ramified at P and infinity. And so in some sense, the endomorphism ring problem still has a lot of geometric information in it because it asks you to write down actual maps, whereas the maximal order problem would be to just look at the algebraic information. It just talks about orders in quaternion algebra, but so it's sort of, I'm not going to be able to go into the details of how those two are equivalent, but that's where the relationship comes from, that the endomorphism ring is isomorphic to a maximal order in a certain quaternion algebra. And so here when, yeah, and there was another question about whether it's okay to just have a single chain from E to E double prime, and the answer is yes. It's just if I have an L power isogeny that's very large, I just want to write it down as a composition of maps, because the N maps separately I can write down. I just wouldn't be able to write down the map of degree L to the N as one map, because that would be too big. Again, it's the same idea when you write a number as a very large number as a product of powers of primes. Sort of those you can like write down with exponents, even though the number is very large. It's the same thing here, that we're decomposing it into like a concatenation of smaller problems. And then sort of the question is, what does that do on the, yeah, with these related problems? Yes?
The uniqueness of finding, like you can find multiple chains from each.
Right. Yep.
You don't get just one of them.
Yeah, and it's sort of, people have shown that sort of all you really need is you need to get your hands on one of them. There might be some of larger degree, smaller degree, right? So there are sort of, the big problem is to just find one to begin with. But you're absolutely right that, for example, SIDH also has some more specifications on them. They want one where the degree is not too big, and but there are some tricks to come around that, get around that. So even though this is not unique, this already captures the main difficulty of the problem. Yeah.
Can I ask one more question related?
Sure.
So the representations of these elliptic curves are going to be using J invariants, right?
Yep.
All of these belong to FP square, but when you're representing them on a computer, you really want like some floating point numbers, no?
Oh, I think you just do arithmetic in a finite field.
Like is ZI lifted to a extension, or is it?
I think you just, I mean, I think in the end, I mean, there are sort of some computational issues I'm sweeping on the rug there. For example, when I say there should be an L-isogeny between the two curves, then I really have to pick curves representing these J invariants and actually write down the isogeny. And so I think sort of what I have, like when we're implementing these things, for example, to test some algorithms that we're doing, what we typically do is like, there's like, you can write down, given a J invariant, you can write down an elliptic curve that has that J invariant and then just sort of work with that. And that just uses finite field arithmetic. I don't think things get lifted to characteristic 0. I don't think that's necessary at that point. Yeah.
I'm asking this because this can be reduced to like a polynomial system, and I'm wondering about the solutions being lifted to a higher field. But yeah, that goes a bit far afield.
Yeah, right. So, well, maybe we can chat about that at the end. So, but yeah, but that's right. So right now, everything is just defined over the finite field. The maps are broken up into these pieces of degree L, and the endomorphism ring question would just ask for 4 of these guys that generate the endomorphism ring as a lattice. And so in joint work with Hallgren, Lauder, Morrison, and Petit, we were able to show, and then generalized by Veselovsky to remove some of the extra heuristics that we still had to use at that point. One can show that under GIH, the endomorphism ring problem and the L-isogeny pathfinding problems are equivalent. And that is under reductions that run in an expected polynomial time. So what does that look like? So you have, I just picked like two of the systems here. So you have SIDH, the key exchange, and the original hash function. They reduce to this L-isogeny pathfinding problem that one can think of as like a graph theoretic problem, because you have some expander graph and you're trying to find a path between two given vertices. We also have an equivalence to the endomorphism ring problem, which I'm going to think of like a arithmetic, sort of both geometric and algebraic information. It's also equivalent to this max order problem, which asks to compute the maximal order inside this quaternion algebra BP infinity that's isomorphic to the endomorphism ring. And that I sort of think about just as an algebraic problem, because the geometry with the actual maps is gone at that point. Then there's also, you can do pathfinding in this quaternion algebra. And that can actually be done efficiently. The only problem is that sort of going between pathfinding in the graph that we really want to analyze and pathfinding in the quaternion algebra, that's reduction, going back and forth between that. It's not known how to do that efficiently. And then several computations also, when we do some of these computations, what also shows up is pathfinding in quotients of Brüher-Titz trees. And so that means there's also like a linear algebra way to view this problem. So it has very many, this L-isogeny pathfinding problem has a lot of different flavors through which people have tried to understand what's going on. And the question is sort of, any of these is it possible to make progress on any of these then? Okay, so that is sort of one big set of reductions that's known. And I had already talked about sort of a second set of isogeny-based systems. The first one being seaside, that was proposed, I think, in 2018. And now these do sort of bring back a little bit of commutativity through group actions. So what's happening in those? We're still working with supersingular elliptic curves. And we want to take some exponential size subset of them. Now, not necessarily all of them anymore. And this time what we want is we want to pick the set X of supersingular elliptic curves in such a way that we can let an abelian group act on them. We want to have an action that we can compute efficiently and that we can't invert easily. So those are the two things that we would like. And so the hardness to invert, that's going to make the scheme secure. So, so that means we will have some set of vertices, and we will be connecting vertices by edges if there's a group element that takes us from the one vertex to the other vertex. So Seaside does this with the class group of a quadratic imaginary field and the set of elliptic curves that are defined over Fp. And so what's interesting about these schemes is that for Seaside, there is a sub-exponential time quantum algorithm, because one can show that inverting the group action can be done if it's possible to solve the abelian hidden shift problem in G, in this case, the class group. And we have Kuperberg's algorithm to solve this abelian hidden shift problem in sub-exponential quantum time. There's a sub-exponential quantum algorithm for solving the abelian hidden shift problem. So that means, for example, for Seaside, there would be a sub-exponential attack. Some of the other schemes that I have mentioned, it's not so clear because these work with class groups of orders that are much bigger, and there are both questions about the efficiency and whether this reduction is so that's not completely understood yet. If this reduction exists for all the schemes that have class group actions, or only for like a subset of them. But so this is another place where quantum algorithms have made progress. And so we can reduce isogenes-based systems that come with a group action to some abelian hidden shift problem. I think, so I'm just stating it very briefly. So we have two functions. G in general is going to be some subgroup of the class group of an imaginary quadratic field that sits inside this quaternion algebra ramified at P and infinity. So, me go back. And but the question of whether the hidden shift problem can be solved in sub-exponential time, it still depends on what the representatives for the group G would even look like, if how big those are. If it's the class group of an imaginary quadratic field, or we heard a talk by Mike Jacobson yesterday about doing class group computations or unit group computations unconditionally, and he mentioned that one of the issues was that even just to get generators, you already need to use GRH, and so here these might be class groups of like orders, and it's not even clear how big these generators would necessarily be if you look at the schemes in like full generality. But so there's the connection between isogeny-based systems that have this group action and the connection to a abelian hidden shift problem. Now, people have sort of tried to sort of find some framework that all of these fit in, some what they call an über-isogeny framework. I don't think their terminology has the umlaut on the U, but and the goal is also to sort of have the group actions encroach, like extend them to cases that were thought to be just on the non-commutative side, meaning that the endomorphism rings are all going to be very big. So this attempt to sort of find a framework that all of these fit under, that's sort of work in progress still. But sort of one question that is possible to answer is, so we have the things like David Zhao and Luca De Feo's singular Diffie-Hellman SIDH. Then we have Seaside with a class group action. Is there one single problem that they all reduce to that we should try to solve here? Yeah, I saw the chat about breaking oocyte, but I'm just mentioning that as a candidate because there are other generalizations of oocyte that are not, I don't want to go into detail about defining all of them. I'm just mentioning them as more generalization of group class group action based schemes, and not all of them have been broken. So, but sort of going back to whether there is one single problem, if breaking that would break all of the schemes that have been proposed, and the answer is yes. If you can compute endomorphism rings of supersingular elliptic curves, then you would be able to break all of the proposed, you would be able to invert group actions and also be able to compute paths in the supersingular L-isogeny graphs. So what does so this is a recent result of Veselovsky that breaking isogeny crypto based on group actions can also be reduced to solving the endomorphism ring problem. And so that means, so we have the picture from before where we had the L-isogeny pathfinding problem that's equivalent to the endomorphism ring problem. And then there are systems that have a class group action, and they can also be broken if the endomorphism ring problem can be solved efficiently. So that means that sort of the hard problem that sits at the center of this would be the endomorphism problem, and that would also be that is also a problem I find really interesting, because it sort of uses the elliptic curve, it uses the geometric algebraic information, and so so if that is the main problem, then what kind of so how hard is this endomorphism ring problem, or what has been done with that so far? So how far away are we from finding an efficient algorithm for computing endomorphism rings of supersingular elliptic curves? Well, the fastest, so I'm in recent work of myself, Holgren, Morrison, Park, and Chris Leonardi, we gave an algorithm for computing endomorphism rings of supersingular elliptic curves that has this running time. It's at this point a classical algorithms. It still uses a bunch of heuristics, unfortunately. And because of this p to the 1/2, it is a fully exponential algorithm. And the bottleneck of the algorithm is that we, in the beginning, need to find endomorphisms, or in other words, cycles in the isogeny graph that generate something of rank 4 inside the endomorphism ring. And just finding cycles in the supersingular isogeny graph, that's already something that nobody knows if that can be done faster than exponential time. So classical and quantum are both exponential time algorithms for that at this point. And the question here that I sort of want to pose at the end of my talk is whether quantum algorithms might have an advantage for doing a problem like cycle finding in an expander graph. So, but whether, so that sort of would be a big problem, or even just something better than p to the 1/2. So let me just summarize what I've talked about today. So supersingular isogeny-based crypto is one of a very small set of candidates that we have for post-quantum crypto. For some schemes, we have a sub-exponential quantum algorithm by reducing it to the abelian hidden shift. And if we found an efficient quantum algorithm or classical algorithm for computing endomorphism rings of supersingular elliptic curves, we could break the proposed systems. But so far, we're very far away from finding something like that. And it would be very interesting to see if quantum algorithms could get an advantage. So, and I'm gonna just leave that as my open question for ending the talk. And so, yeah, I'll end my talk with this question, and thank you for your attention.